All right, everyone, you see the answers to worksheet number 2, questions 1 to 8. I assume we're probably going to have to go over a couple of those questions. Any issues that we want to go over here today? 6 and 7? Okay. Yep. 3, 6, 7. Any others? 3, 6, 7. All right, let's take a look at number 3 then. It says a 1,500 kilogram car. That's our mass. We identify that right away. Accelerates from 55 kilometers per hour to 90 kilometers per hour right away. This is a big one right here, right? We want to identify those non-standard units, those units that we know we're going to have to convert. Let's identify this as a given as well. This is going to be VI, the initial velocity, VF, the final velocity, knowing, of course, that we're going to have to convert them. Looking for impulse. Impulse is delta P, the change in momentum. We don't really have a symbol for impulse that we use. We're just going to use delta P, its definition, the change in momentum. All right. Let's say delta P is equal to F times delta T is equal to M times delta V. Remember, on your data sheet, it just says FT equals MV. It doesn't say delta P equals all that stuff, but we know that it does, right? We know that M times delta V is change in momentum, which is impulse, so we'll just set that equal to delta P ourselves. We want to find delta P. We don't know anything about F and T. We do know the mass and VF and VI, so let's go with that part of the equation. Let's say delta P is equal to M times VF minus VI. Let's do the conversion right now, though. VI, convert it to meters per second, is going to be what? What is that conversion? 55 divided by 3.6, good. 55 divided by 3.6 is 277. Good, let's go to 4 or 5 decimal places like we have here. 5.2778 meters per second. And VF, I believe, is 25 meters per second. Oh, that's 15? Okay. 25 even, right? All right, now that we have our givens converted to meters per second, now we can go and plug them into the equation and do what we need to do. The mass here is 1,500 kilograms. We're going to multiply that by 25 minus 15.2778, and we're going to get our answer that I gave you just a few minutes ago, which was 1.46 times 10 to the 4 Newton seconds. Anybody put different units for the impulse there besides Newton seconds? Is that a valid set of units, by the way? Sure it is. Is there another set of units that I could have used? Kilograms meters per second, right? Impulse and momentum have the same units. They're interchangeable. Kilograms meters per second, Newton seconds. Doesn't really matter which one you use, whatever you're most comfortable with. Just recognize both. Okay, use whichever you want. Recognize both. All right. Next one we wanted to go over was question number 6. This one says a 1.0 kilogram ball traveling towards a soccer player at a velocity of 5 meters per second rebounds off the soccer player. Soccer player is foot at a velocity of 5 meters per second. Mass, what's this one going to be? VI. Is this one going to be VF? Okay. I want to draw attention to something, though, something that I just caught as I was reading that. It rebounds. What's the big deal with that? Why do I want to remember that it rebounds? That the soccer ball is coming towards me and then going away from me. What's the big deal with that? Yes. In other words, one of them is going to have to be positive, one of them is going to have to be negative. Now, it doesn't really matter which one's which. Okay, let's define towards us as positive and away from us as negative. But it doesn't really matter. You could have easily defined it the other way around. You would have just gotten the opposite sign for the force. That's all. It's important to recognize, though, that they are opposite signs because they are two opposite directions. And I think probably those of you who got this wrong, that was probably the major factor why you got this wrong. You forgot to include a negative value in there for one of those. All right, the time of contact is this. We want to find the force, so we want to find F. How do we know this one's impulse? It doesn't say impulse. It doesn't say momentum. It has a force in a time. Right. Sometimes it's obvious, sometimes it's not quite as obvious. Now, at the top of this page, it says impulse. So it stands to reason that in all these questions, you're going to use impulse. But 3 months from now, you may have to do this question where it doesn't say impulse at the top of the page. And you've got to recognize that when you have a force in a time, it's still impulse. All right, let's write down the equation. At least our version of the equation. Okay, we're looking for the force. We've got the time. We've got the mass. And we've got VF and VI. So we'll use the last two parts of the equation, the two parts that actually appear on my data sheet. F times T equals M times delta V. Rearrange that. F is equal to M times delta V over delta T. Remember we had a multiple choice question yesterday where you were asked to find the impulse, but a number of people actually found the impulse and then divided it by time to get the force? You guys remember that? It's pretty common to actually have to rearrange it to solve for force. It is. But be careful you know what you're being asked for, because although it's very common to do what we're doing right now, it's not every time. Yesterday, that wasn't the case. Okay, we got to read the question and know exactly what we're asked for. If it says force, then okay, do it. But if it doesn't, don't just do it automatically because we have to do it often and we get used to it. All right, our mass is 1 kilogram times the change in velocity. Our final velocity, we're going to say, is negative 8.5. Our initial velocity is 5. Had you defined the signs opposite to that, which would have been okay, it would have been 8.5 minus 5. And we would have gotten the same value of answer. We just would have gotten the opposite sign. Negative 8.5 minus 5 is neg 13.5. We multiply that by 1, divide it by 2 times 10 to the negative 2. We're going to end up with a value of negative 675 newtons. Now, as I really quickly check my answer key here, I had positive 675. The reason I had positive 675 is when I did it on my answer key, I defined negative and positive the opposite to that. I said negative when it was coming towards me and positive when it was going away from me. Doesn't matter. Okay. How many people remembered the signs here? The positives and negatives. Okay? How many people defined towards me as positive and away as negative? How many people the other way around? Okay, you all get the right answer, right? Okay, unless you made some silly mistake somewhere. Doesn't matter. Okay? Even right and left, right? We usually define right as positive, left as negative. But it's okay to do it the other way around if, for whatever reason, that's convenient for you. All right, finally, let's take a look at number 7. It says a 1.5 kilogram rock falls from the top of a 10-meter high building and strikes the ground below. What's the impulse experienced by the rock during its fall? We're going to call that HI, or, you know what, in the end, we're probably going to use it as a displacement, delta D. It should say that it falls from rest, where VI would be 0 meters per second. It's not real clear in this question that that's the case, but that's what it was meant to be. We're going to find the impulse experienced during its fall. So we're going to say impulse is equal to F times T again, equals M times delta V again. Probably going to do this. Delta P is equal to M times delta V. We know what VI is. We know what M is. We just need to find out what VF is. We can do that. And we found the momentum of a number of objects when they struck the ground. You remember those questions that we had kind of earlier in the week, the end of last week? Find the momentum of the object as it strikes the ground. We use VF squared is equal to VI squared plus 2AD in order to get that final speed. And when we did that, we would have gotten a final speed of 14.00714. Now, technically, that is the final speed. We want the final velocity. So VF as a velocity, we're going to make it negative 14.00714. All right, mass is 1.5. The final velocity is negative 14 minus 0, the initial velocity. We multiply those two numbers together, and we end up with negative 21 kilograms meters per second. What other units could I have used for that impulse besides kilograms meters per second? Newton seconds, right? I tend to use Newton seconds mostly because, well, sometimes you get a little bit lazy, and Newton seconds is easier to write than kilograms meters per second. But there's no other good reason to do that. Okay, this is just as good. Is that okay? That would be fine, yes, absolutely. If you said down, 21 down, instead of negative 21, that would be absolutely fine. In fact, it's arguably better to say that. But we're not going to lose any sleep over it. If you say negative, it's clear that you mean downward. But certainly the word is fine. All right? Yesterday, we looked at the two qualitative implications of impulse, those two things that could be described or explained by impulse, not mathematically, but just conceptually explained by impulse. The first one was when we had that predetermined impulse. The second one was when we had what I called that non-predetermined impulse, that word that isn't really a word. What was the difference? When did a predetermined impulse typically occur? What's happening when we have that predetermined impulse? Good. When it's stopping, when the object is stopping, we have a predetermined impulse. The impulse of the object is going to be the same no matter how it stops. We don't control that. Okay, we cradle the ball, we do whatever, but that's not changing the impulse whatsoever. When you're stopping an object, it's a predetermined impulse. Now, when do we have the other situation, a non-predetermined impulse, Jesse? Good. Starting an object, or the equivalent of starting an object. We talked yesterday about the baseball, right? When you're hitting the baseball, the ball's coming towards you, and then you're hitting it. So you're not really starting it, because it was already moving, but you're starting it going in the other direction, like you said. So when you're stopping an object versus when you're starting an object. Now, the effect of what you do is completely different in each of these cases. Okay, the idea when you have a predetermined impulse is typically that you want to increase the stopping time. You look at the equation here for a second. Impulse is equal to F times delta t. If I increase the stopping time, let's say we've got an impulse of 10 and a force of 5, what would the time be? 2, right? Let's say I increase the stopping time to 5. The impulse is still going to be 10 because it's a predetermined impulse. What's the force going to be? The force is going to be, not 1, it's going to be 2, right? So by increasing the stopping time, what happens? We decrease the force. That's all because this impulse isn't changing. The impulse was 10 in both cases there. Predetermined impulse, increase stopping time, decrease the force. That's the basic principle behind everything that cushions an impact. Increase stopping time, decrease force. Versus the non-predetermined impulse. When we're trying to start something, usually we're trying to make it go faster and farther, like a golf ball or a baseball. What we're going to do in that case, if we take a look at that equation again, delta P is equal to F times delta T. And we recognize that delta P is not predetermined. Delta P can change. If we increase the force, then the impulse is going to increase as well. If we increase the time of contact, then the impulse is going to increase as well. So by increasing the time here, we're not decreasing the force. Increasing the time has no bearing on the force this time. Increasing the time has only a bearing on the impulse, and we're going to increase it. All right? Make sense? Yesterday we watched the two little videos that kind of helped us to see that a little bit better. The hockey shot video, the idea was the flex in the stick, right? It increased the time of contact with the puck, made the puck go faster. The other one was the ledge jumper video, where the guy jumps off the ledge and onto that air mattress at the bottom of the building. Increase the stopping time of those guys, decrease the force. All good? I told you guys that you're going to get a question almost certainly on your unit test and almost certainly on your diploma exam that asks you about this. There is a smaller but still real possibility that you get one on this. Okay, this is almost for sure. This is 50-50. So remember that, understand that. All right, the only thing that I want to do today is take a quick look at one type of graph. That type of graph that I want to look at is called an F versus T graph, force versus time. And essentially what you've got to remember in this is that the area of this graph is the impulse. It is by far the most important thing that I'm going to teach you today. 3 words. Area equals impulse. Monday, I'm going to give you a quiz on Monday. It won't be on this graph, so it'll be on the concept of impulse. Okay? But Monday, I'm also going to ask you a question in review, not part of the quiz. When you see an F versus T graph, what do you think? That's going to be the exact question. When you see an F versus T graph, what do you think? And your answer is going to be 3 words. Area equals impulse. As soon as you see that graph, I want you to think area equals impulse. Now, there are little things that we've got to remember beyond that, but this is by far the most important thing. One of the things that we've got to be aware of is that there are 2 kinds of areas here. In the graph that I have drawn up there, there's only one. The area is all above the x-axis. That's going to be a positive value of area and therefore a positive value of impulse. But if I have a graph that looks like this, with my line like this, then my area is below the x-axis. When I go to calculate that area, I'm going to make it a negative value. If you happen to have some above and some below, well, then you're going to calculate both and you're going to add them up. And finally, once you've got the area, and you are going to get the area each and every time. Remember, you see that graph, I want you to think automatically area equals impulse. Even if you're not asked for impulse, I want you to think that and do that. But sometimes they take you a step further in the question. They ask you for the change in velocity, not the impulse, not the change in momentum, but the change in velocity. If that's the case, I still want you to get the impulse. I still want you to get it. And then once you've got the impulse, the area, I want you to set that equal to m times delta v. Okay, this is the area. The mass would likely be given to you. All you're going to have to do in that case is rearrange the equation to solve for the change in velocity. So although you're not looking for impulse, you're still going to do the area equals impulse thing to help you get what you actually are looking for, which in this case is the change in velocity. We could do it as take it a step further. If you asked for the final velocity, given an initial velocity, then get the area, which is the impulse, get delta v from that area, and then from delta v, get vf. All right, let's take a look at a quick example. 9.4, page 462. It says a golfer hits a long drive sending a 45.9 gram golf ball, okay, grams, non-standard units, due east. Figure 9.22 shows an approximation of the net force as a function of time. Force versus time, right away, before I even finish reading this question, what do you think? 3 words, right? Area equals impulse. I don't even care what we're asked here. I know that I'm going to end up using this. This area equals impulse. As soon as I see F versus T graph, area equals impulse. What's the impulse provided to the ball? So we're looking for delta P, and we're also looking for the velocity of the ball at the moment the golf club and the ball separate. That's a good question. Okay, so we're looking for VF there. It's a bit of an odd graph if you look at it actually. It looks like the force, as you hit the golf ball, the force is increasing till it reaches a peak value, and then it decreases. Why does it decrease? Why does the force decrease? Yep. No, if the golf club is no longer pushing it, the force would be 0, right? So the golf club is still pushing it. As long as there's a force, the golf club is still pushing on the ball. No, although there would be air resistance, but that's not what it is here. That wouldn't be significant enough to affect it that much. Pardon me? No, it's not slowing down. You got a positive force. So over this entire graph, it's speeding up, right? Even though it's sloped downward in the second half of this graph, it's still a positive force. So it's still going to drive the ball forward. Essentially, yes. Yeah, the ball was reaching the same speed as the golf club. Here's what's happening in the first part of the graph. You're hitting the golf ball. The golf club is in contact with the ball. It's compressing the ball. As the ball gets compressed more and more and more. And by the way, when you hit a golf ball hard, it compresses to almost half its normal size. You don't see it because it happens so quickly. But it compresses to almost half of its normal size. Here's the point where the ball starts moving. Okay? Moving fast. And as it starts moving fast, it starts going away from the club. So what happens? The club's still in contact with it. We want the club to still be in contact with it. But this is the follow-through, where the ball is starting to move faster and faster and faster and faster and faster. So the club isn't keeping up with it as much and isn't pushing quite as hard. You're still pushing on it, but because the ball is now taking off, it's not going to be as hard. Make sense? Is that good? Where does the club actually leave contact with the ball? Position A, B, or C? Position C. Okay? It's not pushing as hard way down here, but it's still pushing right there. Got that? All right. Let's take a look at question A here. What's the impulse provided to the ball? We know area equals impulse. That's the first thing we thought of. As soon as we saw this graph, those 3 words should have came to our mind, area equals impulse. So let's get that area. Now, if you're like me, the first time I did this question, you're going to do twice as much work as you have to do. That's okay. It's not the end of the world, because I still ended up getting the question right. For whatever reason, though, I just didn't do it the short, quick, easy way. Area equals impulse. It's a triangle. So the area of this is simply going to be 1/2 base times height. The base of this goes from 0.1 to 1.1. So the base is going to be 1.0, oops, almost missed this, 1.0 milliseconds, 1.0 times 10 to the minus 3 seconds, times a height of 5,000 newtons. When we multiply those together, I believe we get 2.5 newton seconds, or 2.5 kilograms meters per second. Now, what I did the first time that I ever did this question, I broke it up into 2 sections, found the area of section 1, found the area of section 2, both using the equation 1/2 base times height. I added them together, and guess what I got? 2.5. Well, go figure. Like mathematically, they're both right. We're going to get the same answer. Just that the way I did it the first time was twice as much work, that's all. All right, so I've got the impulse. Now I want to find the velocity at the moment the golf club and ball separate. You guys just told me a minute ago that at this point right here, where the golf club and ball separate, so I'm going to use this impulse over the entire section here, over the entire area. And I'm going to set that impulse equal to m times delta v. I'll rearrange it. Get delta p over m, the impulse over the mass. I get 2.5 over the mass of 0.0459 kilograms. Or you could say 45.9 times 10 to the minus 3. Do the division there, we end up getting 54.5 meters per second. Now, that's the change in velocity. But what speed was this golf ball moving when it all started? 0, right? So the change in velocity is the same as the final velocity here, correct? Is that a hard question? I don't think it is. Okay, I think we can deal with this. If we remember every time we see this graph, every time we see any force versus time graph, even before we know what we're being asked, if we remember that it's area equals impulse, then we got a good start on any question that we're asked. If we're just asked for impulse, well, good. That's it. If we're asked for something further, then use that area to get something further. All right? I'd like you to take a look at page 462, questions 1 and 2. In addition, I'd like you to do worksheet number 2, question number 9. So 3 questions that I'd like you to work on for homework this weekend, please. You got about 6 or 7 minutes right now to work on these. So you get a good chance to get a couple of them, or maybe even all 3 of them finished up here. Okay, let's see what we can do.